Hello, students. Okay, now we're going to get into the nitty-gritty of this AP Physics stuff. Coulomb's law. 1785, a guy named Charles Coulomb experimentally established this fundamental law of force between two stationary charges. And so we're going to look at this, and this is one of the most important parts of our AP study of electrostatics. So let's first take a look at the learning objectives. So the first thing we want to be able to do is to state Coulomb's law and summarize the properties of the electrical forces between the charged particles. Well, our second objective is that we're going to apply Coulomb's law and the superposition principle to system of charged particles. And this is something that tends to give students a little trouble because of the level of the math involved. But we're just going to fall back on our trig, and you're going to be just fine as we do this. So, an electrical force, where we should start, has the following properties. First, is the electrical force is directed along the line between joining the particles. So it's a straight line between the particles. In fact, all the particles that are in the system. And two, it is proportional to the product of the magnitude of the charges and of the particles. And three, it's attractive if the charges are of opposite sign and repulsive if the charges have the same line. Now, this Coulomb's law is a very important law because it's an inverse square law, as we're going to see. So from these observations, Coulomb proposed the following mathematical form of this law. He said that the magnitude of the electrical force between charges Q1 and Q2, and they're separated by a distance r, is equal to K sub E, and this is just a constant, times the absolute value of Q1 and Q2 over the square of the distance between those. And Ke is the constant we're going to call Coulomb's constant. I would like to go back and review with you very quickly. Remember that we're talking about charge and not mass because it's important that we're discussing the charge. So the charge on an electron is going to be negative 1.6 times 10 to the minus 19 coulombs. Okay, and the charge on a proton, we're going to call that electron QE, okay, and QP, the charge of a proton, is going to be positive 1.6 times 10 to the minus 19 coulombs. And remember that the charge on a neutron is 0. So it's very important to remember what the charges are on these particles. You will be given this on the AP exam, by the way. And this law that we're looking at, F equals K, Q1, Q2 over R squared, okay, is known as Coulomb's law. I want to go ahead and give you the value of K. K equals, it's really easy to remember, 9, okay, 9 times 10 to the 9th. And our units are Newton meters squared per Coulomb squared. Okay, and that's a constant, and you're going to see that this will all cancel out to give us, you can see that the meter squared and the meter squared will cancel, and we've got these two charges, coulombs times coulombs, are going to give us Coulomb squared, so that will cancel, leaving us with newtons, and force, remember, is expressed in newtons. And while we're on that topic, remember, when using Coulomb's law, remember that force is a vector quantity, and you have to treat it that accordingly. So we're going to be using our vector addition again, and when we have more than 2 or 3 charges, we're going to have to go back and use that component method of vector addition, if you remember that way back when we were talking about forces. So just like forces, like other forces, electrical forces are going to obey Newton's law, especially Newton's third law. So the force 1 on 2 and force 2 on 1 are equal in magnitude but opposite in direction, right? Okay, so let's review a couple of other things that are going to be important to remember. If you have two like charges, let's say a positive charge and a positive charge, and these are like charges, so they are going to repel each other. Okay, and if you have two unlike charges, say a positive and a negative, then they are going to attract each other, and they will either repel or attract each other with the same force, equal in magnitude, opposite in direction. Now, you may have noticed something. The Coulomb force is very similar to the gravitational force because they both act at a distance without direct contact. Both are inversely proportional to the distance squared, with the force directed along a line connecting the two bodies. The mathematical formula is the same. Gravitation has mass, though, rather than having charge. So let's write that out. So in Newton's law of gravitation, you see that the gravitational force between two objects equals that gravitational constant here, okay, times the product of the masses over the square of the distance between them. Now, notice the gravitational constant is 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. That's very, very small, making the gravitational force a very small force. Where when you have the electrostatic force, the electrostatic force is K, Q1, Q2, let's put the absolute value sign around them, over R squared. And KE, remember, equals 9 times 10 to the ninth Newton meters squared per Coulomb squared. So you can see there are a lot of similarities. They're both inverse square laws, and they're both a result of products of two things. Now, mass and charge are two very, very different things, so they are very different. But Coulomb's law, notice, is times 10 to the ninth, so it's a very, very large force compared to the gravitational force. One very important thing to point out, or a couple of very important things to point out, is there's two really important differences between these two laws. One, remember that electrical forces can be attractive or repulsive. That's very important to remember. Electrical forces can be attractive or repulsive, but gravitational forces are always attractive. And number two, the electrical force between charged elementary particles is much stronger than the gravitational force between the same particles. So remember that. Electrical forces can be attractive and repulsive. Gravity is only attractive, and the electrical force is much stronger than the gravitational force. So let's start with an example. Let's contrast the magnitude of the electrical force and the gravitational force between a proton and an electron. Okay, so to start with, the electron and proton, let's use a hydrogen atom. Okay, so they have a separation distance. We're going to let that be R. Okay, R of about 5.3 times 10 to the minus 11 meters. That's about the distance between a proton, an electron, and a hydrogen atom. So we want to find out what is the magnitude of the electrical force and the gravitational force that exists between each of those when we do it. So then we're going to compute the acceleration caused by the electrical force on the proton. And then we're going to repeat that for the gravitational acceleration. So let's start off by calculating part A. Let's calculate the electrical force. Okay, so for the electrical force, Fe equals, we're going to use Coulomb's law, remember, K. Let's just start off by writing the equation, Q1, Q2 over R squared. Okay, so filling in 9 times 10 to the ninth, that is our K value. And since both have the same charge, we're using the absolute value, and they both have a charge of 1.6 times 10 to the minus 19 coulombs. And since they're alike, we're just going to square that value, Q times Q over Q squared. And the distance between them, they're over R squared. Don't forget to square the distance. This is a very common error that students make. They forget to square the distance. Times 10 to the minus 11 meters, and we're going to square that. Now, I'm going to give you a moment. We're going to plug that into the calculator, and when I'm calculating, when we finish, we come up with a value of 8.2 times 10 to the minus 8 newtons. Okay, that's the force, that's the electrical force between the proton and the electron. And so now we're going to move to the next slide, and we're going to calculate the gravitational force between the two. So in calculating the gravitational force, instead of substituting charge, this time we're going to substitute the mass. And we just look those up. We can use the Google, or we can go to the front of our AP formula guide, and we'll see that the gravitational force, F sub g, equals, this time we're going to use G rather than K, mass of the proton, mass of the electron, over the distance between those two squared. Okay, so we fill in the values, and if you remember, G, again, we can go to our table of values and look this up, is 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. Okay, and multiply that by, well, we're going to start with the mass of the proton. The mass of a proton, again, given on our table of values, 1.67 times 10 to the minus, very small, 27 kilograms. And then the mass of an electron, very small, 9.11 times 10 to the minus 31 kilograms. Very, very small. Okay, and divided by the distance squared, don't forget to square the distance, 5.3 times 10 to the minus 11 meters, and we'll square that. Now, the biggest problem students have with this, not only forgetting to square the distance between them, but also the order of operations. So be very careful when inputting your numbers. Okay, and if you calculate this correctly, we get 3.6 times 10 to the minus 47 newtons. Very, very small force. That's the force of gravitation between the two. Well, the problem actually wants us to contrast those. Let's just put together a ratio and find the ratio of the two forces. So ratio of two forces. Let's do the electrical force Fe to the gravitational force Fg. Okay, and we get the electrical force, let's see, 8.2 times 10 to the minus 8 newtons, and we divide that by the force we just found, 3.6 times 10 to the minus 47 newtons, and of course newtons cancel, and our ratio comes up to be 2.3 times 10 to the 39, which is a very, very large difference. So that is the ratio, 2.3 times 10 to the 39th, okay, times difference, order of magnitude, very, very large. So hold on to your values, and we're going to go on now, and we want to compute the acceleration of the electron caused by the electrical force. Okay, so to do this, we're going to compute the acceleration of the electron caused by the electrical force. We're going to use Newton's second law and the electrical force found in part A. So remember, switch over to the pencil here, the force equals ma. Okay, so we change the acceleration is going to be the electrical force over the mass, which is, the force was 8.2 times 10 to the minus 8 newtons, divided by the mass of the electron, 9.11 times 10 to the minus 31 kilograms. Okay, and if we carry out the proper calculation, we get 9.0 times 10 to the 22nd meters per second squared. Okay, so that is the acceleration of the electron. Okay, and then we'll use the we'll use the force, the gravitational force, to see what that acceleration would be. Same thing here. This one was the electrical force, so here we're going to go for the gravitational force. So Fg divided by the mass, and we get force was 3.6 times 10 to the minus 47 newtons. Boiling over a little bit into the prior answer, over the mass of the electron, 10 to the minus 31 kilograms. Okay. And that's going to give us a an acceleration of 4.0 times 10 to the minus 17 meters per second squared. So you can see the magnitude of the acceleration is also quite different. So the gravitational force between the charged constituents of this atom is negligible compared with the electrical force between them. So the electrical force is so strong, however, that any net charge on an object would quickly attracts nearby opposite charges, and it just neutralizes the object. As a result, gravity is going to play a much greater role in the mechanics of moving objects in everyday life. So just as practice, what I would like for you to do is find the magnitude of the electrical force between two protons separated by 1 femtometer. And I won't make you look that up. I'll tell you what that is. That is actually 10 to the minus 15 meters. That's 10 to the minus 15 meters. And if you remember, that is a very important number. That's where the nuclear strong force starts taking over. That's approximately the distance between two protons in the nucleus of a helium atom. A helium atom. And if the protons were not held together by the strong force, what would be their initial acceleration due to the electrical force between them? Well, I'm going to give you the answer so you know. Remember, that's 10 to the minus 15. I see that that's hard to see, so let me give you the answers. To part A, you're finding the electrical force, and you should get 2 times 10 to the second newtons, or 200 newtons, and B, the acceleration between them would be 1 times 10 to the 29th meters per second squared. That's providing there was no nuclear strong force. And just as a reminder, you're looking for the force between the protons. And the protons, have a charge of 1.6 times 10 to the minus 19 coulombs. Okay, 1.6 times 10 to the minus 19 coulombs, okay, is the charge on the proton. So now we get into the real problems, and these are going to involve what we call the superposition principle. So the superposition principle says when you have a bunch of charges, more than two, that act on a charge of interest, each exerts an electrical force. And what we're going to do is we're going to calculate these electrical forces separately, then we're going to add them as vectors using that component method. So we're going to take a look at an example. So in this example, we've got 3-point charges that lie along the x-axis, okay? And what we want to do is determine the magnitude and the direction of the net electrostatic force on Q1. Now notice that Q1 is in the very center. So what do? Well, in calculating the magnitude of the individual forces, okay, we're going to use Coulomb's law between each of the two charges. So we're going to calculate the force between these two first, and then we're going to calculate the force between these two. And since they're in a line, we can just simply add them. So let's give this a try. So to start with, let's calculate the force between the 3 microcoulomb charge and the 4 microcoulomb charge. Notice microcoulomb means 10 to the minus 6. So we're going to say force on 1 by 2 equals K, Q1, Q2 over R squared. Okay, now let's fill in our values. 9 times 10 to the 9th Newton meters squared per Coulomb squared, okay, times 3 times 10. Micro means negative 6. Okay, coulombs. See if I can fit this in there. Times 4 times 10 to the minus 6. And all that over the square of the distance. Don't forget the square of the distance. 0.20 meters squared. Everything must be in coulombs and meters. So remember, microcoulombs is 10 to the minus 6. So when we do the math, okay, again, make sure you're doing the order of operations correctly. Sorry. Okay, we should get 2.7 newtons of force between those two. Now, let's go ahead and do the second one, the force on 1 by 3. So I'm going to make this much smaller. K, Q1, Q3 over R squared. Okay, filling in the values, 9 times 10 to the 9th Newton meters squared per Coulomb squared. Now, you're not required to put in the units if you don't want, just when you're in the plug-in. 3 times 10 to the minus 6 coulombs, and then 7 times 10 to the minus 6 coulombs, and divide by the distance between those, which is 0.15 meters. Then don't forget to square. And when we do that, do the math appropriately. You can pause and do these with me, which would be a really great idea. I'm going to put a box around that one. Okay, you should come up with 8.4 newtons. So we have the two forces. Now, what we should note is that the charges, they are being attractive. So Q2 is actually pulling Q1 to the left, and Q3 is pulling Q1 to the right. Now, just for sake of convention, I'm going to let to the left be negative and to the right be positive. So in my free body diagram that I've drawn here, you can see to the left I'm just letting be negative. So the first one shows the force on 1 by 2, and the other force, the force on 1 by 3, is in the positive x direction. Okay, we've done the calculations. Now we're going to add those two together. So we're going to add negative 2.7 since that's left, and then 8.4, which is right. Okay, and our answer should be 5.7 newtons to the right. So much like a tug of war there going on. And I'm going to leave you with one last problem. This one is going to be a little bit more difficult here. So in this problem, you see 3 point charges that lie in the XY plane in a vacuum. And what I want you to do is to find the net electrostatic force on charge 1. Here's charge 1. So that is a charge of 4 microcoulombs. See if I can erase that so you can see it. 4 microcoulombs. We're going to find the net force on that charge. Now, in doing that, the very first thing that I would do is I would draw the free body diagram for Q1. And notice that Q1 is being pulled to the right on the positive x-axis to the right, but it's being pulled upward to the northeast, okay, at about 73 degrees. Also, I want you to know the force exerted on Q1 by Q2 is an attractive force because these two charges have opposite signs, and it points along the line between the two charges. The force exerted on Q1 by Q3 is also an attractive force, and it points along the line between Q1 and Q3. Remember, force acts along the line. So Coulomb's law says that the magnitudes of these forces is going to be the vector addition between those two forces. So since the forces point in different directions, we're going to use vector components to find that net force. So on the next slide, let's go ahead and we'll do the math. I'm going to include the drawing because that's just far too much to try to remember here. So let's start and let's do the force between the 4 microcoulomb charge and the 6 microcoulomb charge. We're just going to calculate the magnitude of the force. The direction at this point doesn't matter right now. So again, our formula F equals K Q1, Q2 over R squared. And we're going to fill in the numbers. I'm going to leave the units out this time, just for the sake of room. Okay, don't forget to square the number. And again, pause at this point and see if you can come up with the correct answer. And I'm now punching in on my calculator. I get 9.6 newtons. Okay, that is the force between these two charges. Okay, notice it's along a straight line. Okay, now let's move on and let's do the force between the 4 Coulomb charge and the negative 5 Coulomb charge. So F, write your formula, always do that. Q1, Q2, R squared. 9 times 10 to the 9th times 4 times 10 to the minus 6 coulombs times 5 times 10 to the minus 6 coulombs over the distance between those two charges, which is 0.1 meters, and squared. Don't forget to square it. Pause and calculate. We get 18 newtons. Okay, so far what we've done is we've just calculated the force between the three charges, between the Q1 and Q2 and Q1 and Q3. And just, I'm going to make this Q1 and Q3. That should have been Q3 there. Okay, and so we come up with 9.6 newtons and 18 newtons. Now, what's the next step? Well, the net force is the vector sum of F12 and F13. So now we need to use the component method to calculate the answer. So we're going to go over to the next slide to do that. Now, when we did this earlier, I found, or I always find actually, that making a table makes it so much easier. So I'm going to make a table here. We're going to let the force